Welcome back to the Math Professors. Thanks for joining us. So what we cover are topics that can be found in algebra, pre-calculus, the calculus sequence, statistics, and a lot of more. So if you want to help us grow our channel and we can provide you more free content, please like, subscribe, and share. So today we're going to cover is trig substitutions. And really the superpower of our trig substitutions is that we can write a sum or a difference of squares as a monomial perfect square, and I'll kind of show you how this works. So I consider these, sums and differences of perfect squares, and my goal really is to write this sum of a perfect square as, a monomial that's also a perfect square. And the way we do this is through trigonometry. So what I'm going to use for this particular substitution, I'm going to let x equals a tangent of theta. So now if I have, your a squared plus x squared, well, what I know is I'm going to let x equal this thing. So, this is going to get stuffed in here. So this is going to be equal to a squared plus a tangent of theta all squared. Now, simplifying this, I have a squared plus a squared tangent squared of theta. So we factor out our a squared, and what I'm going to get is 1 plus the tangent squared of theta. And what I know is through a Pythagorean theorem that is nothing more than the secant squared of theta. So this is equal to a squared secant squared of theta, or I can say a secant of theta quantity squared. Similarly, if I want to do this piece, if we have a squared minus x squared, what I know is that in this case I'm going to use x is equal to a sine theta. So this is going to be equal to a squared minus a squared, a sine theta squared. We'll get the square of that. Which means I'm going to square that product. So this is going to be equal to a squared minus a squared sine squared of theta. Factoring out the a squared, and I'm going to get 1 minus the sine squared of theta. Which is probably a much more common, familiar Pythagorean theorem that, sine squared of x plus cosine squared of x is equal to 1. So 1 minus sine squared of x is equal to the cosine squared of x. And that's really where this one comes from as well. You're just taking that Pythagorean theorem and dividing everything by the cosine squared. So this is going to be a squared cosine squared theta. So again, what I have is I have a binomial of squares, and this becomes a monomial that's a perfect square. And similar here, I have a subtraction of two perfect squares, which becomes a monomial of a perfect square. And then similarly here, your x squared minus a squared, where a is going to be equal to the secant of theta. Squared, which means I'm going to square the first, I'm going to square the second. So this is going to be equal to, that's funny. I am substituting in for x. I'm just used to putting in the second spot, so excuse me. So this is going to be equal to x squared minus a squared, x squared minus a squared. So x is going to be this. This is going to be a secant of theta all squared minus a squared. This is going to be equal to a squared secant squared of theta minus a squared. Factoring out your a squared, and you're going to have the secant squared of theta a minus 1. Which is going to be a squared tangent squared. So again, this binomial can be turned into a monomial perfect square. Okay, I want to also talk about our reference triangles and how this is going to be used. So let me pause it. I'm going to erase this side, and we're going to talk about the reference triangles to each one of these pieces, and then eventually we'll do some work on these. So these are the three reference triangles that hold for these three substitutions. And really what we're using for the reference triangles is just the Pythagorean theorem that a squared plus x squared is going to be equal to this hypotenuse squared. So you can see that a squared plus x squared is a squared plus x squared, and when I square that hypotenuse, you're going to have a squared plus x squared. So this is true. And similarly, the square of these legs is going to be equal to the square of the hypotenuse, and the square of the sum of these, the sum of the squares of these legs is going to be equal to the square of the hypotenuse. Now they'll become useful when we're trying to essentially unsubstitute. So what we're going to have is we're going to have essentially the integral of a complicated expression that tends to have, one of these three binomial squares, and we're going to use these as our substitutions. After we're done substituting, simplifying, and then eventually integrating, I'm going to have to substitute or unsubstitute this back into, the original variable x as opposed to the new variable theta. And in order to unsubstitute, we use these reference triangles. So let me come up with an example. It makes a lot more sense in practice. So here's going to be our example. I want to evaluate this integral. So what I have, the integral of 1 over the square root of 9 minus x squared. And what I notice is I have a sum of squares for this binomial. So what I can see is this piece right here is going to become important, which I know is going to be 3 squared plus 9 squared. Now what we know is when we have the form a squared plus x squared, this is a squared plus x squared, what we're going to use is we're going to use x, which is equal to a times the tangent of theta, where a is, whatever the square root of this is, or in this case, you can see a is 3. So this is going to be equal to 3 tangent of theta. So what I want to do is I want to simplify this binomial using this, and then I also want to talk about what we have to do here. So simplifying this binomial, your 9 plus x squared is going to be equal to 9 plus, I don't know why I wrote that as an x, but here we go. So x is going to be equal to 3 tangent of theta all squared. So we can see this is 9 plus 9 tangent squared of theta, which I can factor out that 9, which is 1 plus the tangent squared of theta. And we know that 1 plus tangent squared of theta is equal to the secant squared of theta. So this is going to be equal to 9 secant squared of theta. All right. So what that allows me to do is allows me to substitute this 9 plus x squared and turn it into 9 secant squared of x. Now I can't just substitute, the radicand expression. I also have to substitute for the differential. So really this is kind of an advanced u substitution. Now u would be equal to, some piece, I'd say u would be equal to, say, this thing, so I also have to find du. Now instead of it being u, what we're really using is this, essentially. So if I substitute for x, I also have to substitute for dx. So the derivative of the tangent is going to be equal to the secant squared of x. So this is going to be 3 secant squared of, theta, d theta. So now substituting everything back in here. What I know is 9 plus x squared is the same thing as 9 secant squared. So this is going to be the integral of 1 over the square root of. Again, let's do this in colors to make sure that this piece right here is equal to this. So that's going to be equal to 9 secant squared theta. And then what I do know also is that dx, your dx is equal to this piece right here. So this is going to be times 3 secant squared of theta d theta. All right, now let's simplify this up as much as I can. So this is going to be equal to the integral. Well, this is the square root of a perfect square, which is going to, doesn't really cancel these things. It technically becomes the absolute value, but a lot of times you're integrating these things over the interval for which it's positive. So we do know that this is going to be 3 secant of theta in absolute value, and then the top is going to be equal to 3 secant squared of theta d theta. Now what we're going to assume is that the interval for which you're integrating is going to verify that this part is positive, so we're just going to drop the absolute values here. Okay. Now simplifying, we can see that the 3's cancel, one of the secants cancel, so this is going to be equal to the integral of the secant of theta d theta. And we know how to integrate that thing. If you wanted the integral of the secant of theta d theta, what you can do is you can multiply top and bottom of this by secant of theta plus tangent of theta, secant of theta plus tangent of theta, d theta. So then this is the integral of the secant squared of theta plus secant of theta tangent of theta all over the secant of theta plus tangent of theta. And this just ends up being a u, like u is your denominator, so u is equal to the secant of theta plus tangent of theta. And then du is going to be the derivative of the secant, which is equal to the secant of theta tangent of theta. And the derivative of the tangent is going to be the secant squared of theta d theta. So what we can see is this thing just integrates to, simplifies through that substitution as 1 over u du which is going to be equal to the natural log of the absolute value of u, or the natural log of u, which is the secant of theta plus tangent of theta. Of course, plus c. So that's what this ends up being. This ends up being the natural log of the secant of theta plus the tangent of theta plus c. Now, what we've done here is we've found its integral, but its integral is in terms of my substitution variable, really kind of like before it'd be in terms of u, right? This is in terms of u, so this is the natural log of u plus c, so now I have to unsubstitute, right? So this was the natural log of the absolute value of u, but I have to plug in u. I have to unsubstitute. So for the same reason, I have to do this here as well. So in order to unsubstitute these things, I have to draw my reference triangle, and then I can figure out what these things are in terms of x. So my reference triangle, I guess I'll put it over here. So the reference triangle is going to look like this. This is going to be equal to theta. And what I know is, this is kind of an easier way to figure out how you do your reference triangle, that if I solve for the tangent of theta, your tangent of theta is going to be equal to x over 3, which we know is going to be opposite over adjacent. So I know that, that this is going to be equal to x, and this is going to be equal to 3. Which means that this is going to be equal to that square root of that binomial. This is going to be equal to the square root of 3 squared plus x squared, or 9 plus x squared. What's kind of interesting is when you set up your reference triangle, you're going to use a particular trig function. So just kind of remember that what trig function is what. So the tangent is going to be opposite over adjacent. So that this is going to be the square root of that binomial that you're going after. It happens most every time. So now this is going to be equal to the natural log. Well, the secant of theta, well, I know the cosine is going to be adjacent over hypotenuse. So the secant is going to be a hypotenuse over adjacent. So this is the square root of 9 plus x squared all over the adjacent, which happens to be 3. Plus, again, the tangent of theta we already know is going to be opposite over adjacent, which is going to be x over 3 plus c. Now, that's a fine answer. There's nothing really wrong with that. But a lot of times your book won't write that as an answer when you're looking in the back. And the reason why is, this is common denominator. So I can say 9 plus x squared plus x all over 3 plus c. And we know that a property of logarithms says that if I have the log of a quotient, it's the subtraction of those logarithms. So this is going to be the natural log of the square root of x, 9 plus x squared, plus x. And then I'm going to have minus the natural log of the absolute value of 3, which is going to be 3. And I still have a plus c. Now you'll see that your answer will just say this thing plus c, because the negative natural log of 3 and c is still c. So this is going to be the natural log of the absolute value of 9 plus x squared plus x, and then finally, plus, let's say a different c, plus c, so constant. All right, let me give you another example that uses a different substitution. All right, so here's our next example. And in the previous example, I forgot to write something like this, and I'll kind of explain where that comes from. This tends to force the absolute value of the expression to just be dropped, because the expression will be positive there. So I'll make sure to put that in here for this one. So what I want to do is I need to essentially go after that binomial, so we can see that that binomial is going to be y squared minus 25. So that's what my substitution is going to have to be. And we know that if we have that y squared minus 25, that this is of the form y squared minus 5 squared. Which means I'm going to have to do a substitution where it's going to use the secant. So it's of this form. This is going to be equal to a secant of theta. So what I'm going to do is I'm going to let this thing be equal to, I'm going to let y equal a secant of theta. I'm trying to fit this in here with this piece right here. So what we're going to do is we're going to let y equal 5 secant of theta. And let's see what happens to this expression right here. So we're going to have 5 secant of theta squared minus 25. So this is 25 secant secant squared of theta minus 25. So then factoring out the 25, this is going to be secant squared of theta minus 1. And we know that that is going to give us the tangent squared. Pause those pictures. So 25 tangent squared of theta. Okay, now remember that I have to substitute all my expressions for your y, and then also my expressions for dy. So if y is equal to this, then dy is going to be the derivative of that, or the differential of this is going to be the differential. So the derivative of the secant of theta is going to be secant of theta tangent theta. So this is secant of theta. I'm going to have to pull this down. It is way too big. So dy is going to be equal to 5 secant of theta tangent of theta d theta. Okay. So let's plug everything in that I know. So I know that this, the blue part, is going to be equal to that expression. We also know that y is equal to this expression. And then finally our dy is going to be equal to the substitution for the differential. So this is going to be equal to this piece here. All right, so let's substitute everything in. So this is going to become the integral of the square root of, well, I know y squared minus 25. This, using the substitution, is this, which simplifies to 25 tangent squared of theta. Now this also was, the expression cubed, but this is going to be my y expression, which is y is 5 secant of theta cubed. So I guess I'll put that in blue as well, because I'm using the same formula for that. So this is going to be 5 secant of theta, all being cubed. And then what I know is that dy is going to be equal to 5 secant of theta, tangent of theta, d theta. So now I've substituted everything in the integrand and also substituted the differential. So now I can simplify and see what happens here. So the square root of this is would be the absolute value, but we're restricted to y bigger than 5. So that means this is going to give us the integral of 5 tangent of theta. And on the bottom, we're going to have 125 secant cubed of theta. And then here I'm going to have times 5 secant of theta, tangent of theta, finally d theta. Of course, that's over 1. So let's see what simplifies here. I know that one of the secants are going to cancel, and I'm going to get 2 of those tangents. So this is going to be, 2 factors of the tangent. So this is going to be equal to 5 times 5. I'm going to cancel these. So that's 25, and that is 25 times 5. So this will just become 5 on the bottom. One of the secants will cancel, so this will become a 2. And then I'll have 2 factors of tangent. So this is going to be equal to tangent squared of theta all over secant squared of theta. I still have a 5, so I'm going to pull out that 1/5, and this is going to be d theta. All right, simplifying this. What I know is that this is going to be sine squared of theta over cosine squared of theta, so 1/5. I have sine squared of theta over cosine squared of theta. And on the bottom, I have 1 over cosine squared of theta. So you can see that those cosines are going to cancel. So this is going to be equal to 1/5 times the integral of the sine squared of theta, d theta. Now, in order to integrate the sine squared, I did a video on that recently. We are going to have to use this, a double angle formula, 1 minus the cosine of 2 theta all over 2. Or I can say 1/2 times 1 minus the cosine of 2 theta. So I can pull out that 1/2, so now this is going to be equal to 1/5 times 1/2, the integral of this expression, 1 minus the cosine of 2 theta d theta. And then simplifying these things, this is going to be equal to 1/10. And the integral of 1 is going to be equal to theta. And the integral of the cosine of 2 theta is going to be, well, negative. That cosine is going to be negative sine of 2 theta over 2, or 1/2 the sine of 2 theta. Finally, plus c. All right, so I've integrated this, but remember this is in terms of theta, not in terms of the original variable. So let's set up our reference triangle over here and kind of talk about what's happening. So taking this formula right here is going to help us, figure out the legs of that triangle, because this says the secant of theta is going to be equal to y over 5. Or I can say, if you like this better, the cosine of theta is going to be equal to 5 over y. So cosine being the adjacent over the hypotenuse. So the adjacent over the hypotenuse. Which means this leg is going to be the square root of, really, this binomial. And then you can just verify. This squared plus this squared is this squared. Okay, so the problem is this will work for the sine of theta, the cosine of theta, the tangent of theta, and so on. What do I do with the sine of 2 theta? Well, what I know is the sine of 2 theta can be written as 2 sine theta cosine theta, which means those 2's will cancel. So this is going to be equal to 1/10 times theta minus the sine of theta cosine of theta. Now remember, since this is a triangle of theta, not a triangle of 2 theta, I needed to do that in order to simplify this. So now let's plug these things in. So this is going to be 1/10. How do I know what theta is? Well, you can use one of these two pieces. You need to know what theta is, you can just use the inverse trig function. So you can say theta is equal to the cosine inverse of 5 over y. Or if you choose, if you prefer the secant, this is going to be the secant inverse of y over 5. It's kind of your choice, or equivalent, right? I'll use the cosine inverse because it's more familiar and used more often. So this is going to be the cosine inverse of 5 over y. Minus the sine of theta is going to be opposite over hypotenuse. So this is going to be equal to the square root of y squared minus 25 over the hypotenuse, which is going to be y, times the cosine of theta, which is going to be 5 over y, plus c. And then we can simplify this the best we can. Cosine 5 over y, I'm pretty pleased with this. So what we're going to finally get here is this is going to be equal to 1/10. I guess this was a fine enough answer right there, but we'll just write it together. 5 over y minus 5 root y squared minus 25 all over y squared plus c. And if we really want to get, even more anal with this simplification, you can multiply this by 1/10. You can multiply this by 1/10. So this will be squishing this in. This is going to be 1/10 cosine inverse of 5 over y. 5 goes to the 10 twice, so this is going to be minus the square root of y squared minus 25 all over 2y squared plus c. So many students like to see as many examples of this as possible, because you can see this is kind of messy and try to keep track of all your substitutions and then all your unsubstitutions. So I'm going to make one more video after this one, just doing a couple extra examples if you'd like to see it. So please consider liking, subscribing, and sharing. Thank you.